Hi class. So here is the second way that we can get air to rise. It's called orographic lifting. Orographic lifting takes place when there is a physical barrier, such as a mountain, that obstructs the airflow. So the air can't go around the mountain, it can't go underneath the mountain, it's got to go over the mountain. Okay, and so in this particular case, we've got, like the Pacific Ocean, air coming off the Pacific Ocean. It encounters the physical barrier, the mountain, and it's going to have to rise up over the mountain. Okay, and so now all of those processes that we've talked about before come into play. So the air ascends, and maybe we should keep in mind here that the air is ascending. It might be stable. The air might be stable. It wants to stay at the Earth's surface. It has no reason to rise other than the mountain is in the way, and it has to rise. So in this particular case, you can actually get stable air and force it to rise. In this example, because of orographic lifting. Okay, so when it does rise, the air ascends, the pressure decreases. When the pressure decreases, the air expands. When the air expands, the density decreases. When the density decreases, the temperature decreases. So hopefully you're getting this process down, these steps. When the temperature decreases, okay, it's first going to decrease at the dry adiabatic collapse rate. As long as the air is unsaturated, it's going to cool as it rises at the dry adiabatic collapse rate. Remember, that is 10 degrees C per 1,000 meters. Okay. Now, let's assume that at some point, as the air rises above the mountain, it reaches saturation. So we form a cloud base. Okay. And again, this is called the LCL. Okay, that's where the cloud base occurs. All right, and so as a reminder, at the LCL, all kinds of interesting things are going on. So that's where saturation occurs. Okay. If saturation occurs, that means the relative humidity is 100%. If the relative humidity is 100%, that means that the mixing ratio equals the saturation mixing ratio. If the mixing ratio equals the saturation mixing ratio, then the dew point temperature equals the air temperature. Okay. When you hit the LCL, this is also where condensation occurs. If condensation is occurring, then literally the water vapor is condensing into liquid water droplets. Okay, so we're going, and that is, in that process, we're going to release 600 calories of energy for every gram of water that is condensed. Okay, again, that is literally releasing heat energy into the atmosphere. So you're going to slow down the rate of cooling. So the rate of cooling was at 10 degrees C per 1,000 meters. Okay, and once you hit the LCL, the air is still going to cool as it rises, but it's going to cool at a slower rate. So we're going to switch to the moist adiabatic collapse rate, which is, again, it varies depending on where you are, but we're going to use 5 degrees C per 1,000 meters. Okay, so that's orographic lifting, but I think I'll take this opportunity, since we haven't drawn anything on the right-hand side of this figure, the air's got to come back down the mountain, and so and I guess maybe what I should say before that is, so this is called the leeward side of the mountain. Okay, so when the air goes up the leeward side of the mountain, okay, so that's where all the clouds are, that's where all the precipitation is, and this tends to be very green. Okay, with all the precipitation they get, there's lots of vegetation on the leeward side of the mountain. Okay, when you come down the other side of the mountain, we got all of the same processes going on, but in reverse. Okay, and so on the leeward side of the mountain, the air descends down the mountain. When the air descends, the pressure increases. When the pressure increases, the air compresses. Okay, when the air compresses, the density increases. When the density increases, the temperature is going to increase. So temperature increases as air flows down the mountain due to the compression that's taking place. Okay, and we haven't mentioned for a while is as the temperature increases, that means the saturation mixing ratio is increasing. And if the saturation mixing ratio is increasing, that means the relative humidity is decreasing. So this side of the mountain is this is called the leeward side. Sorry, this should have been the windward side. I blew that. This is the windward side. I apologize for steering you guys off in the wrong way. So the windward side of the mountain tends to be green. The leeward side of the mountain, this tends to be pretty barren. Pretty brown, pretty barren. Okay, it gets a little moisture, a little precipitation, and so that leads to it being brown. Think of tumbleweeds on this side. So think of the Rocky Mountains. So in New Mexico, Colorado, Wyoming, Montana, the leeward side of the Rocky Mountains tends to be really dry. Okay, and so as a result, very brown, very pretty desolate, not much vegetation, scrub brush, cacti, that sort of thing. So, so I apologize for the mislabeling here. The windward side is the green side. That's where the air is going up. The leeward side is where the air is coming down, and that's where you get compressional warming taking place, and as a result, pretty barren features on the leeward side. All right, coming up next is going to be frontal wedging.